The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So welcome back. So we're now moving to a new chapter, which is going to have a little more of a statistical flavor when it comes to designing methods, right? Because if you think about it, okay, some of you have probably attempted problem number 2 in the problem set, and you realize that maximum likelihood estimators does not give you super trivial estimators, right? I mean, when you have an n theta theta, then the thing you get is not something you could have guessed before you actually attempted to solve that problem. And so, in a way, we've seen already sophisticated methods. However, in many instances, the maximum likelihood estimator was just an average, and in a way, even if we had this confirmation from maximum likelihood that indeed that was the estimator that maximum likelihood would spit out, and that our intuition was therefore pretty good, most of the statistical analysis or use of the central limit theorems, all these things actually did not come in the building of the estimator, in the design of the estimator, but really in the analysis of the estimator. And you could say, well, if I know already that the best estimator is the average, I'm just going to use the average. I don't have to basically quantify how good it is. I just know it's the best I can do. When we're going to talk about tests, and we're going to talk about parametric hypothesis testing. So you should view this sentence as parametric means, well, it's about a parameter like we did before. And hypothesis testing is on the same level as estimation. And on the same level as estimator will be the word test. Okay? And when we're going to devise a test, we're going to actually need to understand random fluctuations that arise from the central limit theorem better. Okay, it's not just going to be in the analysis. It's also going to be in the design. And everything we've been doing before in understanding the behavior of an estimator is actually going to come in and be extremely useful in the actual design of tests. Okay? So as an example, I want to talk to you about some real data. I will not study this data, but this data actually exists. You can find it on R. And so it's the data from the so-called Credit Union Cherry Blossom Run, which is a 10-mile race. It takes place every year in DC. Seems that some of the years are pretty nice. 2009, there were about 15,000 participants, pretty big race. And the average running time was 103.5 minutes. All right, so about an hour and a half or a little bit more. And so you can ask the following question, right? This is actual data, right? 103.5 actually averaged the running time for all of 15,000. Now, this in practice might not be something very suitable, and you might want to just sample a few runners and try to understand how they're behaving every year without having to collect the entire data set. And so you could ask the question, well, let's say my budget is to ask for maybe 10 runners what their running time was. I still want to be able to determine whether they were running faster in 2012 than in 2009. Why do I put 2012 and not 2016? Well, because the data set for 2012 is also available. And so if you were interested and you know how to use R, just go and have fun with it. So, so to answer this question, what we do is we select n runners, right? So n is a moderate number that's more manageable than 15,000 from the 2012 race at random. That's where the random variable is going to come from, right? That's where we actually inject randomness in our problem. And we're going to denote this, guys, by, we're going to denote, so remember, this is an experiment. So really, in a way, the runners are the omegas. And I'm interested in measurements on those guys. So this is how I have a random variable. And this random variable here is measuring their running time. Okay? If you look at the data set, you have all sorts of random variables you could measure about those random runners. Country of origin, I don't know, height, age, a bunch of things. Okay? Here, the random variable of interest being the running time. Okay, everybody understand what the process is? Okay, so now I'm going to have to make some modeling assumptions. And here I'm actually pretty lucky. I actually have all the data from a past year. I mean, this is not data from 2012, which I also have, but I don't use. But I can actually use past data to try to understand what distribution do I have, right? I mean, after all, running time is going to be rounded to something. Maybe I can think of it as a discrete random variable. Maybe I can think of it as the exponential random variable. Those are positive numbers. I can think, I mean, there's many kind of running times that could come up to mind, many kind of distributions I could think of for this modeling part. But it turns out that if you actually plot the histogram of those running times for all 15,000 runners in 29, you actually are pretty happy to see that it really looks like a bell-shaped curve, which suggests that this should be a Gaussian. So what you go on to do is you estimate the mean from past observations, which was actually 103.5, as we said. You estimate the variance, which was 373. And you just try to superimpose the curve with this one, which is a Gaussian PDF. With mean 103.5 and variance 373, and you see that they actually look very much alike. And so here, you're pretty comfortable to see that the running time actually is Gaussian distribution. All right, so now I know that the x1 to xn, I'm going to say they're Gaussian. OK? I still need to specify two parameters. So what I want to know is the distribution the same from past years, right? So I want to know if the random variable that I'm looking for, if I say pick one, say x1, does it have the same distribution in 2012 that it did in 2009? Okay? And so the question is x1 has a Gaussian distribution with mean 103.5 and variance 373. Is that clear? OK? So this question that calls for a yes-no answer is a hypothesis testing problem. I'm testing a hypothesis. And this is the basis of basically all of data-driven scientific inquiry. You just ask questions. You formulate a scientific hypothesis. Knocking down this gene is going to cure melanoma. Is this true? I'm going to collect. I'm going to try. I'm going to observe some patients on which I knock down this gene. I'm going to collect some measurements. And I'm going to try to answer this yes/no question. Okay? It's different from the question, what is the mean of the mean running time for this year? OK, so this hypothesis testing is testing if this hypothesis is true. The hypothesis in mathematical terms, I mean, in common English, we just said, was the running time, were runners running faster? Right? Anybody can formulate this hypothesis. Now, you go to a statistician, and he's like, oh, what you're really asking me is x1 normally has a Gaussian distribution with mean less than 103.5 and variance 373, right? That's really the question that you ask in statistical terms. And so if you're asking if this was the same as before, there's many ways it could not be the same as before. There's basically three ways it could not be the same as before. It could be the case that x1 is not equal to one in expectation to 103.5, so the expectation has changed, or the variance has changed, or the distribution has changed. I mean, who knows? Maybe runners are now just all running, holding their hands, and it's like now a point mass at one given point. OK, so you never know what could have changed. Now, of course, if you allow for any change, you will find change. And so what you have to do is to factor in as much knowledge as you can, make as many modeling assumptions so that you can let the data speak about your particular question. Here, your particular question is, are they running faster? So you're only really asking a question about the expectation. You really want to know if the expectation has changed. So as far as you're concerned, you're happy to make the assumption that the rest has been unchanged. OK? And so this is the question we're asking. Is the expectation now less than 103.5? Because you specifically asked whether runners were going faster this year. Right? They tend to go faster rather than slower. All right? OK? So this is the question we're asking in mathematical terms. So of course, when I did that, I need to basically fix the rest. And fixing the rest is actually part of the modeling assumptions. So I fix my variance to be 373. OK? I assume that the variance has not changed between 2009 and 2012. Now, this is an assumption. It turns out it's wrong. So if you look at the data from 2012, this is not the correct assumption. But I'm just going to make it right now for the sake of argument. OK? And also the fact that it's Gaussian. Now, this is going to be hard to violate, right? I mean, where did this bell-shaped curve come from? Well, it's just natural when you just measure a bunch of things. The central limit theorem appears in the small things of nature. I mean, that's the bedtime story you get about the central limit theorem, and that's why the bell-shaped curve is everywhere in nature. It's just the sum of little independent things that are going on. And this Gaussian assumption, even if I wanted to relax it, there's not much else I can do, and it is pretty robust across the years. All right, so the only thing that we did not fix is the expectation of x1, which now I want to know what it is. And since I don't know what it is, I'm going to call it mu, and it's going to be a variable of interest. All right, so it's just a number mu. Whatever this is, I can try to estimate it, maybe using maximum likelihood estimation, probably using the average, because this is Gaussian, and we know that the maximum likelihood estimator for a Gaussian is just the average. And now we only want to test if mu is equal to 1 of 3.5, like it was in 2009, or on the contrary, if mu is not equal to 1 of 3.5, and more specifically, if mu is actually strictly less than 1 of 3.5. That's the question you asked. Now, why am I writing mu equal to 1 of 3.5 and not, or is less than 1 of 3.5 rather than equal to 1 of 3.5 versus not equal to 1 of 3.5? It's because since you asked me a more precise question, I'm going to be able to give you a more precise answer. And so if your question is very specific, are they running faster? I'm going to factor that in, the fact what I write. If you just ask me, is it the same? I'm going to have to write, or is it different than 1 of 3.5? And that's less information about what you're looking for. OK? So by making the modeling, all these modeling assumptions, the fact that the variance isn't changed, the fact that it's still Gaussian, I've actually reduced the number of, and I put numbers in quotes because this is still an infinite of them, but I'm limiting the number of ways the hypothesis can be violated. The number of ways, the number of possible alternative realities for this hypothesis. All right? For example, I'm saying there's no way mu can be larger than 1 of 3.5. I've already factored that in. OK? It could be, but I'm actually just going to say that if it's larger, all I'm going to be able to tell you is that it's not smaller. I'm not going to be able to tell you that it's actually not, that it's actually larger. OK? So, and the only way it can be rejected now, the only way I can reject my hypothesis is if x belongs to a very specific family of distributions. If it has a distribution which is Gaussian with mean mu and variance 373 for mu, which is less than 1 of 3.5. All right, so we started with basically was x1. So that's the reality. x1 follows n 1 of 3.5, 373. OK, and this is everything else. Right, so for example, here is x follows some exponential, I don't know, 0.1. OK, this is just another distribution here. Those are all the possible distributions. What we said is we said, OK, first of all, let's just keep only those Gaussian distributions. Right? And second, we said, well, let's look only at among those Gaussian distributions, let's only look at those that have, well, maybe this one should be at the boundary, say. Let's only look at the Gaussians here. So this guy here are all the Gaussians with mean mu and variance 373 for mu less than 103.5. OK? So when you're going to give me data, I'm going to be able to say, well, am I this guy or am I one of those guys, rather than searching through everything. And the more you search, the easier for you is to find something that fits better the data, right? And so if I allow everything possible, then there's going to be something that just by pure randomness is actually going to look better for the data. OK? So, right, so for example, if I draw 10 random variables, right, if n is equal to 10, then, and let's say they take 10 different values, then it's actually more likely that those guys come from a discrete distribution that takes each of this value with probability 1 over 10 than actually some Gaussian random variable, right? It would be perfect. I can actually explain it. If the 10 numbers I got were, say, 90, let's say I collect 3, 90, 95, and 102, then the most likely distribution for those guys is the discrete distribution that takes 3 values, 91 with probability 1/3, 95 with probability 1/3, and 102 with probability 1/3, right? That's definitely the most likely distribution for this. So if I allowed this, I would say, oh no, this is not distributed according to that. It's distributed according to this very specific distribution, which is somewhere in the realm of all possible distributions. Okay? So now we're just going to try to carve out all this stuff by making our assumptions. Okay, so here in this particular example, just like make a mental note that what we're doing is that a little birdie told me that the reference number is 103.5. Okay? That was the thing I'm actually looking for. In practice, it's actually seldom the case that you have this reference for yourself to think of, right? Maybe here I just happen to have a full data set of all the runners of 2009. But if I really just asked you, I said, were runners faster in 2012 than in 2009? Here's $10 to perform your statistical analysis. What you're probably going to do is call maybe 10 runners from 2012, maybe 15 runners from 2009, ask them and try to compare their mean. There's no standard reference. You would not be able to come up with this 103.5 because this data maybe is expensive to get or something. Okay, so this is really more the standard case, all right, where you really compare two things with each other, but there's no like actual ground truth number that you're comparing it to. Okay, so we'll come back to that in a second. I'll tell you what the other example looks like. So let's just stick to this example. I tell you it's 103.5, okay? Let's try to have our intuition work the same way. We said, well, you know, taking averages worked well. The average should tell me over these 10 guys, should tell me what the average should be, what the mean should be. So I could just say, well, X bar is going to be close to the true mean by the law of large number. So I'm going to decide whether X bar is less than 103.5 and conclude that in this case, indeed, mu is less than 103.5 because those two quantities are close. Right? I could do that. The problem is that this could go pretty wrong because if n is small, then I know that xn bar is not equal to mu. I know that xn bar is close to mu, but also know that there's pretty high chances that it's not equal to mu. In particular, I know it's going to be somewhere at 1 over root n away from mu, right? 1 over root n being the root n coming from what? CLT, right? That's the root n that comes from CLT. CLT tells us, I mean, you know, in blunt words, CLT tells me the mean is at distance 1 over root n from the expectation, pretty much. Right? That's what it's telling. So 1 over root n, you know, if I have 10 people in there, 1 over root 10 is not a huge number, right? It's like 1/3 pretty much. Okay, so 1/3, 103.5, if the true mean was actually 103.4, but my average was telling me it's 103.4 plus 1/3, I would actually come to two different conclusions, right? So we know that, so let's say that mu is equal to 103.4. Okay, so that's, you're not supposed to know this, right? That's the truth, hidden truth. Okay, now I have n is equal to 10. So I know that x bar n minus 103.4 is something of the order of 1 over square root of 10, which is of the order of, say, 0.3. Okay? Okay, so here this is all hand-wavy, okay? But that's what the central limit theorem tells me. What it means is that I can have, it is possible that x bar n is actually equal to, sorry, 103.4, is actually equal to 103.4 plus 0.3, which is equal to 103.7. Which means that while the truth is that mu is less than 103.5, then I would conclude that mu is larger than 1 over 3.5. Okay? And that's because I have not been very cautious. Okay? So what we want to do is to have a little buffer to account for the fact that xn bar is not a precise value for the true mu. It's something that's 1 over root n away from mu. And so what we want is the better heuristic that says, well, if I want to conclude that I'm less than 1 over 3.5, maybe I need to have be less than 1 over 3.5 minus a little buffer that goes to 0 as my sample size goes to infinity. And actually, that's what the law of large number tells me. But the central limit theorem actually tells me that this should be true, something that goes to 0 as n goes to infinity at the rate 1 over root n. Right? That's basically what the central limit theorem tells me. So to make this intuition more precise, we need to understand those fluctuations. We need to actually put in something that's more precise than this like little wiggles here. Okay? We need to actually have the central limit theorem come in. So here's the example of comparing two groups. So pharmaceutical companies use hypothesis testing to test if a drug is efficient, right? That's what they do. They want to know, does my new drug work? And that's what the Federal Drug Administration Office is doing on a daily basis. They ask for extremely well regulated clinical trials on 1,000 people and check, does this drug make a difference? Did everybody die? Does it make no difference? Should people pay $200 for a pill of sugar, right? So that's what people are actually asking. So to do so, of course, there's no ground truth about, so there's a placebo effect. So it's not like actually giving a drug that does not work is going to have no effect on patients. It will have a small effect, but it's very hard to quantify. We know that it's there, but we don't know what it is. And so rather than saying, oh, the ground truth is no improvement, the ground truth is the placebo effect, and we need to measure what the placebo effect is. All right, so what we're going to do is we're going to split our patients into two groups. And there's going to be what's called a test group and a control group. So the word test here is used in a different way than hypothesis testing, so I will just call it typically the drug group. All right, and so I will refer to mu drug in this for this guy. Okay, so now let's say this is a cough syrup. Okay, and when you have a cough syrup, what you want to measure, let's say the way you measure the efficacy of a drug syrup of a cough syrup is to measure how many times you cough per minute. Okay. And so if I define mu control, the number of expectorations per hour, not per minute, but per hour. So I have just the expected number, right? This is a number I don't know because I don't have access to the entire population of people who will ever take this cough syrup. And so I will call it mu control for the control group. So those are the people who've been actually given just like sugar, like maple syrup. And mu drug are those people who are given the actual syrup. Okay? And you can imagine that maybe maple syrup will have an effect on expectorations per hour just because, well, it's just sweet and it helps. Okay? And so we don't know what this effect is going to be. We just want to measure if the drug is actually having just a better impact on expectorations per hour than the just pure maple syrup. Okay? So what we want to know is if mu drug is less than mu control. That would be enough. If we had access to all the populations that will ever take the syrup for all ages, then we would just measure, did this have an impact? And even if it's a slightly ever so small impact, then it's good to release this cough syrup, assuming that it has no side effects or anything like this, because it's just better than maple syrup. Okay? The problem is that we don't have access to this. And we're going to have to make this decision based on samples that give me imprecise knowledge about mu drug and mu control. So in this case, unlike the first case where we compared a known expected value to a fixed number, which was 103.5, here we're just comparing two unknown numbers with each other. Okay, so there's two sources of randomness, trying to estimate the first one and trying to estimate the second one. Okay? All right, before I move on, I just wanted to tell you, I apologize. One of the graders was not able to finish grading his problem sets for today. So for those of you who are here just to pick up their homework, feel free to leave now. Even if you have a name tag, I will pretend I did not read it. All right. OK, so I'm sorry, you'll get it on Tuesday. And this will not happen again. All right, so OK. So for the clinical trials, now I'm going to collect information. I'm going to collect data from the control group, and I'm going to collect data from the test group. All right? So my control group here, I don't have to collect the same number of people in the control group than in the drug group. Actually, for cough syrup, maybe it's not that important. But you can imagine that if you think you have the cure to a really annoying disease, it's actually hard to tell half of the people you will get a pill of nothing. Okay? People tend to want to try the drug. They're desperate. And so you have to have this sort of imbalance between who's getting the drug and who's not getting the drug. Okay, so it's not, and people have to qualify for the clinical trials. There's lots of fluctuations that affect what the final numbers of people who are actually going to get the drug and are going to get the control is going to be. And so it's not easy for you to make those two numbers equal. You'd like to have those numbers equal if you can, but not necessarily. And by the way, this is all part of some statistical science called design of experiments. And in particular, well, you can imagine that if one of the series had higher variance, you would want to collect more people in this group than the other group. Yeah.
Sorry. So when we're subtracting like something that approaches 0 as an approaches infinity, we're like effectively making it hard for the hypothesis to be satisfied.
Yeah.
So like that's on purpose.
Yeah, that's on purpose. And I'll come to that in a second. All right. So, so basically, we're going to make it, if your answer is this true, we're going to make it as hard as possible, but no harder for you to say yes to this answer. Because, well, we'll see why. OK, so so now we have two set of data, the x's and the y's. The x's are the ones for the drug, and the y's are the data that I collected from the people who were just given a placebo. OK? And so they're all IID random variables. And here, since it's a number of expectorations, I'm making a blunt modeling assumption. I'm just going to say it's Poisson, and it's characterized only by the mean mu drug or the mean mu control. OK? I've just made an assumption here. It could be something different. But let's say it's a Poisson distribution. So now what I want to know is to test whether mu drug is less than mu control. We said that already. But the way we said it before was not as mathematical as it is now. Now we're actually making a test on the parameters of Poisson distribution, whereas before we're just making tests on like expected numbers. Okay? So the heuristic, again, if we try to apply the heuristic now, rather than comparing mu x bar drug to some fixed number, I'm actually comparing x bar drug to some control. But now here I need to have something that accounts for not only the fluctuations of x bar drug, but also for the fluctuations of x bar control. OK? And so now I need something that goes to 0 when all those two things go to infinity. And typically, it should go to 0 with 1 over square root of n drug and 1 over square root of n control. OK? That's what the central limit theorem for both x bar drug and x bar control, two central limit theorems, are actually telling me. OK, and then we can conclude that this happens. And as you said, we're trying to make it a bit harder to conclude this because, let's face it, if we were actually using the simple heuristic, right? So let's assume now that we have, for simplicity, right? So let me assume that I have, so I can rewrite x bar drug less than x bar control minus this something that goes to 0. I can write it as x bar drug minus x bar control less than something negative, OK? This little something, OK? So now let's look at those guys. This is the difference of two random variables. From the central limit theorem, they should be approximately Gaussian each. And they're actually, we're going to think of them as being independent, right? There's no reason why the people in the control group should have any effect on what's happening to the people in the test group. Those people probably don't even know each other. And so when I look at this, this should look like some n0 with some mean and some variance that say I don't know what it is. Okay? The mean I actually know. It's mu drug minus mu control. Okay? So if I were to plot the PDF of this guy, it would look like this. I would have something which is centered at mu drug minus mu control. And would look like this, OK? Now, let's say that mu drug is actually equal to mu control. That this pharmaceutical company is a huge scam, and they really are trying to sell bottled maple syrup, bottled corn syrup for $200 a pop, OK? So this is a huge scam, and the true things are actually equal to 0. So this thing is really centered about 0, OK? Now, if we were not to do this, then basically half of the time, I would actually come up with a distribution that's above this value, and half of the time I would have something that's below this value, which would mean that half of the scams would actually go through FDA if I did not do this. So what I'm trying to do is to say, well, OK, you have to be here, so that there's actually a very low probability that just by chance you end up being here. OK? And we'll make all the statements extremely precise later on. But I think the drug thing makes it interesting to see why you're making it hard, because you don't want to allow people to sell things like that. OK, so let's just, before we go more into the statistical thinking associated to tests, let's just see how we would do this quantification, right? I mean, after all, this is what we probably are the most comfortable with at this point. So let's just try to understand this thing. And I'm going to make the statistician's favorite test, which is the thing that obviously you do at home all the time, every time you get a new quarter, is testing whether it's a fair coin or not. All right, so this test, of course, exists only in textbooks. And I actually did not write this slide. I was lazy to just replace all this stuff by the cherry blossom run. So you have a coin. Now you have 80 observations, x1 to x80. So n is equal to 80. I have x1, xn, IID, Bernoulli, p. And I want to know if I have a fair coin. So in mathematical language, I want to know if p is equal to 1/2. And in this case, it's kind of hard to say. Sorry, let's say this is just the heads, OK? And a biased coin, well, maybe you would potentially be interested whether it's biased one direction or the other. But not being a fair coin is already somewhat of a discovery, OK? And so you just want to know whether p is equal to 1/2 or p is not equal to 1/2, OK? Now, if I were to apply the very naive first example to not reject this hypothesis, if I run this thing 100 times, 80 times, I would need to see exactly 40 heads and 40 tails. Now, this is very unlikely to happen exactly, OK? You're going to have close to 40 heads and close to 40 tails. But how close should those things be, OK? And so the little something is going to be quantified by exactly this, OK? So now here, let's say that my experiment gave me 54. Did I do it? Well, let's say heads. Yeah. It's 54? Yeah. Heads, which means that my xn bar is 54 over 80, which is 0.68. All right. All right. So I have this this estimator. Looks pretty large, right? It's much larger than 0.5. So it does look like, my mom would certainly conclude that this is a biased coin for sure, because she thinks I'm tricky. All right. So the question is, can this be due to chance? Right? Can this be due to chance alone? Like, what is the likelihood that a fair coin would actually end up being 54 times on heads rather than 40? OK? And so what we do is we say, OK, I need to understand what is the distribution of the number of times it comes on heads. And this is going to be binomial, but it's a little annoying to play with. So we're going to use the central limit theorem that tells me that xn bar minus p divided by square root of p1 minus p is approximately distributed as an n01. And here, since n is equal to 80, I'm pretty safe that this is actually going to work. OK, so now let's just be a little more. And I can actually use Slutsky here and put xn bar here. Okay, Slutsky tells me that this is OK to do. All right, so now I'm actually going to compute this. So here I know this. This is square root of 80. This is 0.68. What is this value here? We'll talk about it. Well, we're trying to understand what happens if it is a fair coin, right? So if fair, then P is equal to 0.5, right? So what I want to know is what is the likelihood that a fair coin would give me 0.68? Let me finish. All right, so what is the likelihood that a fair coin will allow me to do this? So I'm actually allowed to plug in P to be 0.5 here. Now your question is, why do I not plug in P to be 0.5? But you can. All right, I just want to make you plug in P at one specific point, but you're absolutely right. What you can look at is, right, so OK, let's forget about your question for 1 second. So now I'm going to have to look at xn bar minus 0.5 divided by xn bar 1 minus xn bar. Then this thing is approximately Gaussian, n0, 1, if the coin is fair. Otherwise, I'm going to have a mean which is not 0 here. Right? If the coin is something else, whatever I get here, right? So if my coin, let's just write it for 1 second. Well, actually, let's answer your question first. It's actually going to be easy. Well, I'm not sure. OK. Let's do it. So what is the distribution of this if P, so that's P is equal to 1/2, 0.5. OK? Now if P is equal to 0.6, then this thing is just, well, I know that this is equal to square root of n x n bar minus 0.6 divided by xn bar 1 minus xn bar square root plus, well, now the difference, so square root of n 0.6 minus 0.5 divided by square root of xn bar 1 minus xn bar. Right? Now, if P is equal to 0.6, then this guy is n0, 1. But this guy is something different. Right? This guy is just a number that depends on square root of n. It's actually pretty large. So if I want to use the fact that this guy has a normal distribution, I need to plug in the true value here. Now, the implicit question that I got was the following. It says, well, if you know what P is, then what's actually true is also this. If P is equal to 0.5, then not only, since I know that root n xn bar minus P divided by square root of P 1 minus P is some n0, 1, it's also true that square root of n xn bar minus 0.5 divided by square root of 0.5, 1 minus 0.5 is n0, 1. Right? I know what P is. I'm just going to make it appear. OK? And so what's actually nice about this particular Bernoulli experiments is that I can check if my assumption is violated by checking whether I'm actually, so what I'm going to do right now is now to check whether this is likely to be a Gaussian or not, right? And there's two ways I can violate it, by violating the mean, but also by violating the variance. And here what I did in the first case, I said, well, I'm not allowing you to check whether you violated the variance. I'm just plugging whatever variance you're getting. Whereas here, I'm saying, well, there's two ways you can violate it, and I'm just going to factor everything in. OK, so now I can plug in this number. So this is square root. So this is 80. This is 0.68. So I can compute all this stuff. I can compute all this stuff here as well. And what I get in this case, if I put the xn bar 1, I get 3.45. OK? And now I claim that this makes it reasonable to reject the hypothesis that P is equal to 0.5. Can somebody tell me why? 3 is pretty big. Yeah, 3 is pretty big. So it's very unlikely. So, right, so this number that I should see should look like the number I would get if I asked a computer to draw one random Gaussian for me, right? This number, when I draw one random Gaussian, is actually a number with 99.9%. This number will be between -3 and 3. With 78%, it's going to be between -2 and 2. Okay, so those are actually between, with 70% is basically, 68% is between -1 and 1, and with like 90% is between -2 and 2. So getting a 3.45 when you do this is extremely unlikely to happen, which means that you would have to be extremely unlucky for this to ever happen. Now, it can happen, right? It could be the case that you flip 180 coins and 80 of them are heads. With what probability does this happen? 1/2 to the 80, right? Which is probably better off playing the lottery with this kind of odds, right? I mean, this is just not going to happen, but it might happen. So we cannot remove completely the uncertainty, right? It's still possible that this is due to noise, but we're just trying to make all the cases that are very unlikely go away. Okay? And so now I claim that 3.45 is very unlikely for a Gaussian. So if I were to draw the PDF of a Gaussian, of a standard Gaussian, right? So N01, right? So that's PDF of N01. 3.73 is basically here. Okay? So it's just like too far in the tails. Understood? Now, I cannot say that the probability that the Gaussian is equal to 373 is small. Right? I just cannot say that because it's 0. And it's also 0 for the probability that it's 0, even though the most likely values are around 0. Right? It's the continuous random variable. So it's going to take any probability, any value you give me, it's going to happen with probability 0. So what we're going to say is, well, the fluctuations are larger than this number. The probability that I get anything worse than this is actually extremely small. Right? Anything worse than this is just like farther than 3.73. And this is going to be what we control. All right? So in this case, I claim that it's quite reasonable to reject the hypothesis. Is everybody OK with this? Everybody find this shocking, or everybody has no idea what's going on? Do you have any questions? Yeah.
Regarding the use of p1 minus p as opposed to xn, if you use p1 minus p as 0.5, then you're dividing by a larger number than you would if you used xn. So it feels like our true number is not 3.45, but something a little bit smaller than 3.45, or the distribution to actually be like 1/2. Because it seems like we're adding an unnecessary extra error by using xn bar, and we're adding an error that makes it seem that our result was less likely than it actually was.
That's correct. And you're right. You should prefer. So OK, I didn't want to plug in the p everywhere, but you should plug in it everywhere you can. That's for sure. OK? So let's agree on that. And that's true that it makes the number a little bigger. Did you compute how much we would get if we put 0.5 there? Right? I mean, it's probably easy, right? Well, I don't know what square root of 80 is. Can somebody compute quickly what? I'm not asking you to do it, but like what I want is 2 times square root of 80 times 0.18. What? 3.22. OK. I can make the same cartoon picture with 3.22. And I would be. But you're right. This is definitely more accurate, and I should have done this. I didn't want to just get the confused message. OK? All right. So now here's a second example that you can think of. So now I have 30 times. I toss it 30 times, still in the realm of the central limit theorem. I get 13 heads rather than 15. So I'm actually much closer to being exactly at half. So let's see if this is actually going to give me a plausible value. And what I get is that, so I get 0.33 in average. If the true was 0.5, I would get something like 0.77. And now I claim that 0.77 is a plausible realization for some standard Gaussian. Okay? Now 0.77 is going to look like it's here. And so that could very well be something that just comes because of randomness. And again, if you think about it, if I told you you were expecting 15, you saw 13, you're happy to put that on the account of randomness. Now, of course, the question is going to be, where do I draw the line, right? Is 12 the right number? Is 11? Is 10? What is it? And so we're going to have, what we're going to do, so basically the answer is, it's whatever you want to be. The problem is it's hard to think on the scale, right? What does it mean to think on the scale? If I can think on this scale, I'm going to have to think on the scale of 80 of them. I'm going to have to think on the scale of like running 100 coin flips. And so this scale is moving. It's a moving target all the time. Every time you have a new problem, you have to have a new scale in mind, and it's very difficult. The purpose of statistical analysis, and in particular this process that takes your X bar and turns it into something that should be standard Gaussian, allows you to map the value of X bar into a scale that is the standard scale of the Gaussian. All right? Now, all you need to have in mind is what is a large number or an unusually large number for a Gaussian. That's all you need to know. Right? So here, by the way, 0.77 is not this one because it was actually negative 0.77. So the other one should, so it's this one. OK, so I can be on the right or I can be on the left. But they are still plausible, of 0, but they are still plausible. All right, so understood, like you could actually have in mind all the values that are plausible for a Gaussian and those that are not plausible and draw the line based on what you think is the right number. So how large should a positive value of a Gaussian to become unreasonable for you? Is it 1? Is it 1.5? Is it 2? Stop me when I get there. Is it 2.5? Is it 3? What?
Doesn't that depend on our prior? Like, let's say we already had really good evidence this coin was fair. Like,
yeah, so this is not Bayesian statistics, so there's no such thing as a prior right now. We'll get there. You'll have your moment during one short chapter. Right, so there's no prior here, right? It's really a matter of what do you think is a Gaussian large or not. It's not a matter of coins. It's not a matter of anything. Now I've just reduced it to just one question. So forget about everything we just said. And I'm asking you, when do you decide that a Gaussian is too large to be a reasonable, a number is too large to be reasonably drawn from a Gaussian? And this number is 2, or 1.96. And that's basically the number that you get from this quantile. We've seen the 1.96 before, right? It's actually Q alpha over 2 for alpha is equal to 5%. That's a quantile of a Gaussian. So actually, what we do is we map it again. So we're not the Gaussians, and then we map it again into some probabilities, which is the probability of being farther than this thing. And now probabilities we can think. Probability is something that quantifies my error, and the question is what percentage of error am I willing to tolerate? And if I tell you 5%, that's something you can really envision. What it means is that if I were to do this test 1,000,000 times, 5% of the time, I would expose myself to making a mistake. All right, that's all it would say. If you said, well, I don't want to account for 5%, maybe I want 1%, then you have to move from 1.96 to 2.5. And then if you say I want 0.01%, then you have to move to an even larger number. So it depends, but stating this number, 1%, 5%, 10%, is much easier than stating these numbers, 1.96, 2.5, et cetera. So we're just putting everything back on the scale. All right, so here is, to conclude, this again, as we said, does not suggest that the coin isn't fair. Now, it might be that the coin isn't fair. We just don't have enough evidence to say that. And that goes back to your question about why are we siding with the fact that we're making it harder to conclude that the runners were faster. And this is the same thing. We're making it harder to conclude that the coin is biased. Because there is a status quo. And we're trying to see if we have evidence against the status quo. The status quo for the runners is they ran the same speed. The status quo for the coin can probably all agree is that the coin is fair. The status quo for a drug, I mean, again, unless you prove me that you're actually not a scammer, is that you're actually, the status quo is that this is maple syrup. There's nothing in there. Why wouldn't you? I mean, if I let you get away with it, you would put maple syrup. It's just your corn syrup because it's cheaper. All right? OK. So now let's move on to math. All right? So when I start doing mathematics, I'm going to have to talk about random variables and statistical models. And here, there's actually a very simple thing, which is that it actually goes back to this picture, which is a test is really asking me if I'm on one side of, if my parameter is in some region of the parameter set or another region of the parameter set, right? Yes, no. And so what I'm going to be given is a sample x1, xn. I have a model. And again, those can be braces, depending on the day. And so now I'm going to give myself theta 1 and theta 2. Sorry, theta 0 and theta 1, two disjoint subset. OK, so I have my, right, so capital theta here is the space in which my parameter can live. To make two disjoint subsets, I could just split this guy in half, right? But I'm actually going to make myself, I'm going to say, well, maybe it's this guy and this guy. OK, so this is theta 0, and this is theta 1. What it means, when I split those two guys, I'm actually, in test, I'm actually going to focus only on theta 0 or theta 1. And so it means that a priori, I've already removed all the possibilities of theta being in this region. What does it mean? Go back to the example of runners. This region here for the cherry blossom run is the set of parameters where mu was larger than 103.5. Right? We removed that. We didn't even consider this possibility. We said either it's less. Sorry, that's mu equal to 103.5. And this was mu less than 103.5. OK? But these guys were like, if it happens, it happens. I'm not making any statement about that case. All right? So now I take those two subsets. And now I'm going to give them two different names because they're going to have an asymmetric role. H0 is the null hypothesis, and H1 is the alternative hypothesis. H0 is the status quo. H1 is what is considered typically as scientific discovery. So if you're a regulator, you're going to push towards H0. If you're a scientist, you're going to push towards H1. If you're a pharmaceutical company, you're going to push towards H1. OK? And so depending on whether you want to be conservative, oh, I can find evidence in a lot of data. As soon as you give me 3 data points, I'm going to be able to find evidence. That means I'm going to tend to say, oh, it's H1. But if you say, oh, you need a lot of data before you can actually move away from the status quo, that's H0. OK? So think of H0 as being status quo, H1 being some discovery that goes against the status quo. All right, so if we believe that the truth data is either in one of those, what we say is we want to test H0 against H1. OK, this is actually wording. So remember, because this is how your questions are going to be formulated. And this is how you want to probably communicate as a statistician. So you're going to say, I have the null and I have an alternative. I want to test H0 against H1. I want to test the null hypothesis against the alternative hypothesis. OK? Now, the two hypotheses I forgot to say are actually this. H0 is that theta belongs to theta 0. And H1 is that theta belongs to theta 1. OK, so here, for example, theta was mu. And that was mu equal to 103.5. And this was mu less than 103.5. OK? So typically, they're not going to look like thetas and things like that. They're going to look like very simple things where you take your usual notation for your usual parameter, and you just say, in mathematical terms, what relationship they should be satisfying. Right? For example, in the drug example, that would be mu drug is equal to mu control. And here, that would be mu drug is less than mu control. Right? The number of expectorations is less than for people who take the drug for the cough syrup is less than the number of expectorations of people who take the corn syrup. Okay? So now what we want to do is, so we've set up our statistical hypothesis, or we set up our hypothesis testing problem, sorry. You're a scientist. You've set up your problem. Now, what you're going to do is collect data, and what you're going to try to find on this data is evidence against H0. And the alternative is going to guide you into which direction you should be looking for evidence against this guy. All right? And so, of course, the narrower the alternative, the easier it is for you because you just have to look at one possible candidate, right? But typically, H1 is a big group, like less than. Nobody tells you it's either 103.5 or 103. People tell you it's either 103.5 or less than 103.5. Okay? And so what we want to do is to decide whether we reject H0. So we look for evidence against H0 in the data. Okay? So as I said, these guys, H0 and H1, do not play a symmetric role. It's very important to know which one you're going to place as H0 and which one you're going to place at H1. Because you're going to always favor, in case of sort of, if it's a close call, you're always going to side with H0. Okay? So you have to be careful about this. You have to keep that in mind, that if it's a close call, if data does not carry a lot of evidence, you're going to side with H0. And so you're actually never saying that H0 is true. You're just saying I did not find evidence against H0. So you don't say I accepted H0. You say I failed to reject H0. Okay, and so one of the things is that you want to keep in mind when you're doing this is this innocent until proven guilty. So if you come from a country like America, there's such a thing. And in particular, lack of evidence does not mean that you are not guilty, right? O.J. Simpson was found not guilty. He was not found innocent, okay? And so this is basically what happens. Is like, the prosecutor brings their evidence, and then, the jury has to decide whether they were convinced that this person was guilty of anything. And the question is, do you have enough evidence? But if you don't have evidence, it's not the burden of the defender to prove that they're innocent. Nobody's proving they're innocent. I mean, sometimes it helps. But you just have to make sure that there's not enough evidence against you. Okay? And that's basically what it's doing. You're H0 until proven H1. So how are we going to do this? Well, as I said, the role of estimators in hypothesis testing is played by something called tests. And a test is a statistic. Can somebody remind me what a statistic is? Yeah. Yeah, that's actually just one step more. So it's a function of the observations, and we require it to be measurable. And as a rule of thumb, measurable means if I give you data, you can actually compute it. Okay? If you don't see a soup or an inf, you don't have to think about it. All right, and so what we do is we just have this test, but now I'm actually asking only from this guy, this test, a yes/no answer, which I can code as 0 or 1, right? So as a rule of thumb, you say that, well, the test is equal to 0, then H0, the test is equal to 1, then H1. And as we said, is that if the test is equal to 0, it doesn't mean that H0 is true. It means that I failed to reject H0. And if the test is equal to 1, I reject H0. Okay? So I have two possibilities. I look at my data. I turn it into a yes/no answer. And the yes/no answer is really H0 or H1. Okay? Which one is the most likely, basically? All right. So in the coin flip example, our test statistic is actually something that takes value 0, 1. And any function that takes value 0, 1 is an indicator function. Okay, so an indicator function is just a function. So there's many ways you can write it, but so it's a 1 with a double bar. If you are uncomfortable with this, it's totally okay to write I of something, like I of A. Okay? And that's what? So A here is a statement. Like, an inequality, an equality, some mathematical statement, okay? Or not mathematical. I mean, A can be, my grandma is 20 years old, okay? And so this is basically 1 if A is true, and 0 if A is false. Okay? That's the way you want to think about it. So just this function takes only 2 values, and that's it. And it basically, it's just, so, right? So here's the example that we had. We looked at whether the standardized xn bar, the one that actually is approximately n01, was larger than something in absolute value, either very large or very small but negative. Okay? So we wanted to know, if I'm going back to this picture, we wanted to know if this guy was either to the left of something or to the right of something. Right? Was it in this regions? Now, this thing here, this indicator, I can view this as a function of x bar. What it does, it really splits the possible values of x bar, which is just a real number, right, in 2 groups. The groups on which they lead to a value which is 1, and the groups on which they lead to a value which is 0, right? So what it does is that I can actually think of it as the real line, x bar, and there's basically some values here where I'm going to get a 1, maybe I'm going to get a 0 here, maybe I'm going to get a 0, maybe I'm going to get a 1. I'm just splitting all possible values of x bar, and I see whether they spit out a psi which is 0 or which is 1. Now in this case, it's not clear, right? I mean, the function is very nonlinear. It's x bar minus 0.5 divided by square root of x bar 1 minus x bar. If we put the p in the denominator, that would be clear. That would just be exactly something that looks like this. If x bar the function would be like this. It would be 1 if it's smaller than some value, less than 0 if it's in between 2 values, and then 1 again. Right? So that's psi. Okay? So it starts at, so this is 1, right? This is 1, and this is 0. So if x bar is too small or if x bar is too large, then I'm getting a value 1. But if it's somewhere in between, I'm getting a value 0. Now, if I have this weird function, it's not clear how this happens. Okay? I mean, right? So the picture here that I get is that I have a weird nonlinear function. Right? So that's x bar. That's square root of n x bar n 0.5 divided by square root of x bar n 1 minus x bar n. Right? That's this function. A priori, I have no idea what this function looks like. I mean, OK, I can probably analyze this function, but let's pretend we don't know. So it's like some crazy stuff like this. And all I'm asking is whether in absolute value, it's larger than c, which means that is this function larger than c or less than minus c? So the values on which I'm going to say 1, the intervals on which I'm going to say 1 are this guy, this guy, this guy, and this guy. Okay, and everywhere else I'm saying 0. Everybody agrees with this? This is what I'm doing. Now, of course, it's probably easier for you to just package it into this nice thing that's just either larger than c in absolute value or less than c. You don't want to have to plot this function. In practice, you don't have to. Now, this is where I'm actually claiming. So here I actually define to you a test, and I promise starting this lecture by saying, oh, now we're going to do something better than computing averages. Now I'm telling you, well, just compute an average. And the thing is, the test is not just the specification of this x bar. It's also the specification of this constant c. All right? And the constant c was exactly where our belief about what a large value for a Gaussian is, that's exactly where it came in. So this choice of c is basically a threshold at which we decide above this threshold, this is unlikely to come from a Gaussian. Below this threshold, we decide that it's likely to come from a Gaussian. So we have to choose what this threshold is based on what we think likely means. All right? So just a little bit more of those things. So now we're going to have to characterize what makes a good test, right? Because think of, well, I'll come back to it in a second. But you could have a test that says reject all the time. And that's going to be a bad test, right? The FDA is not implementing a test that says, yes, all drugs work. Now let's just go to Aruba, okay? So people are trying to have something that try to works all the time. Now FDA is not either saying, let's just say that no drugs work, and let's go to Aruba, all right? They just try to say the right thing as often as possible. And so we're going to have to measure this. So the things that are associated to a test are the rejection region. And if you look at this x in En, such that psi of x is equal to 1, this is exactly this guy that I drew. The values of the sample, so here I summarize the values of the sample into their average. But the values of the sample that I collect that will lead to a test that says 1. All right, so this is the rejection region. If I collect a data point, technically I have, right, so I have e to the n, which is a big space, like this. Right, so that's e to the n. Think of it as being the space of xn bars. And I have a function that takes only value 0 or 1. So I can decompose it into this part where it takes value 0 and the part where it takes value 1. And those can be super complicated, right? I can have things like this. I can have some weird little islands where it takes value 1. I can have some islands where it takes value 0. I can have some weird stuff going on. But I can always partition it into the value where it takes value 0 and the value where it takes value 1. And the value where it takes 1, if psi is equal to 1, this is called the rejection region of psi. Okay? So that's just the samples that would lead me to rejecting. And notice that this is the indicator of the rejection region. Right? The test is the indicator of the rejection region. So there's two ways you can make an error when there's a test. Either the truth is in H0 and you're saying actually it's H1, or the truth is in H1 and you say it's H0. And that's how we build in the asymmetry between H0 and H1, is that we control only one of the two errors and we hope for the best for the second one. So the type 1 error is the one that says, well, if it is actually the status quo, but I claim that there's a discovery, if it's actually H0, but I claim that I'm in H1, then I commit a type 1 error. Okay? And so the probability of type 1 error is this function alpha of psi, which is just the probability of saying that psi is equal to 1 when theta is in H0. Now the problem is that this is not just a number because theta is just like moving all over H0, right? There's many values that theta can be, right? So theta is somewhere here. Oh, I erased it, okay. So, right, so for simplicity, we're going to think of theta as being mu and 1 of 3.5, okay? And so I know that this is theta 1, and this was just this point here was theta 0. Okay? Agreed? This is what the cherry blossom run. Now here, in this case, it's actually easy. My function, I need to compute this function alpha psi, which is maps theta in theta 0 to p theta of psi equals 1. So that's the probability that I reject when theta is in H0. Then there's only one of them to compute because theta can only take this one value. So this is really 1 of 3.5. Okay, so that's the probability that I reject when the true mean was 1 of 3.5. Now, if I was testing whether if H0 was this entire guy here, all the values larger than 1 of 3.5, then I would have to compute this function for all possible values of theta in there. And guess what? The worst case is when it's going to be here, because it's so close to the alternative that that's where I'm making the most error possible. And then there's the type 2 error, which is defined basically in the symmetrical way. It's the function that maps theta to the probability. So that's the probability of type 2 error. It's the probability that I fail to reject H0, right? Psi is equal to 0. I failed to reject H0. But that's for theta that actually came from H1. OK? So in this example, that's clear. If I'm here, like if the true mean was 100, I'm looking at the probability that the true mean is actually 100, and I'm actually saying it was 103.5, or it's not less than 103.5. Yeah.
I'm just a little confused by the notation.
Yeah.
You say that big theta sub 1 arrow r. I'm not sure what that notation means.
Well, it means it's a function that maps theta 0 to r. You've seen functions, right?
Yes.
OK. So that's just the way you write. So you typically write something like, so that means that's a function f that goes from, say, r to r, and that maps x to x squared. OK, so here I'm just saying I don't have to consider all possible values. I'm only considering the values on theta 0. The value that it takes, I put r, actually. I could restrict myself to the interval 0, 1, because those are probabilities. So it's just telling me where my function comes from and where my function goes to. And beta is a function, right? So beta psi of theta is just the probability that theta is psi theta, that theta is equal to 1. And I could define that for all thetas. Sorry, that psi is equal to 0 in this case. And I could define that for all thetas, but the only ones that lead to an error are the thetas that are in H1. Otherwise, I mean, I can define this function. It's just not going to correspond to an error. OK? And the power of a test is the smallest. So the power is basically 1 minus an error, 1 minus the probability of an error. So it's the probability of making a correct decision. OK? So it's the probability of making a correct decision under H1. That's what the power is. But again, this could be a function, right? Because there's many ways I can be in H1 if H1 is an entire set of numbers. For example, all the numbers that are less than 103.5. And so what I'm doing here, when I define the power of a test, I'm looking at the smallest possible of those values. OK? So I'm looking at this function, 1 minus. OK, so maybe I should actually expand a little more on this. OK, so beta psi of theta is the probability under theta that psi is equal to 0, right? That's the probability for theta in H1, in theta 1, which means under the alternative that I fail to reject. And I really should, because theta was actually in theta 1. OK? So this thing here is the probability of type 2 error. Now, this is 1 minus the probability that I did reject, and I should have rejected. Right? That's just the law of the complement. Because if psi is not equal to 0, then it's equal to 1. So now if I rearrange this, it tells me that the probability that psi is equal to 1, this is actually 1 minus beta psi of theta. OK? So that's true for all thetas in theta 1. And what I'm saying is, well, so this is now a good thing, right? This number being large is a good thing. It means I should have rejected, and I rejected. I want this to happen with large probability. And so what I'm going to look at is the most conservative choice of this number, right? Rather than being super optimistic and say, oh, but indeed, if theta was actually equal to 0, then I'm always going to conclude that, I mean, if mu is equal to 0, everybody runs in 0 seconds, then I should definitely, with high probability, I'm going to make no mistake. But really, I should look at the worst possible case. OK, and so what I'm looking at is basically the smallest value it can take on theta 1 is called power of psi, power of the test psi. OK, so that's the smallest possible value it can take. All right, so I'm sorry, this is a lot of definitions that you have to sink in, and it's not super pleasant, but that's what testing is. There's a lot of jargon. Those are actually fairly simple things. Just maybe you should get a sheet for yourself and say, these are the new terms that I learned. What is there? Test, rejection region, probability of type 1 error, probability of type 2 error, and power. And just make sure you know what those guys. Oh, and null and alternative hypothesis. OK? And once you know all these things, you know what I'm talking about. You know what I'm referring to. And this is just jargon, but in the end, those are just probabilities, and I mean, those are natural quantities. Just for some reason, people have been used to using different terminology. So just to illustrate when do I make a type 1 error and when do I not make a type 1 error. So I make a type 1 error if H0 is true and I reject H0, right? So the off-diagonal blocks are when I make an error. When I'm on the diagonal terms, H1 is true and I reject H0, that's a correct decision. When H0 is true and I fail to reject H0, that's also the correct decision to make. So I only make errors when I'm in one of the green blocks, in the red blocks. And one block is the probability is the type 1 error, and one other block is the type 2 error. That's all it means. Okay? So you just have to know which one we called 1. I mean, we could have, this of course was pretty, I mean, this was chosen in a pretty ad hoc way. So to conclude this lecture, let me ask you a few questions. In a US court, the defendant is found either, let's just say for the sake of discussion, innocent or guilty. All right, it's really guilty or not guilty, but let's say innocent or guilty. Okay. When does the jury make a type 1 error? Yeah. And he's guilty? And he's innocent, right? The status quo, everybody's innocent until proven guilty. So that's our H0 is that the person is innocent. And so that means that H0 is innocent. And so we're looking at the probability of type 1 error. So that's when we reject the fact that it's innocent. So we conclude that this person is guilty. Okay, so type 1 error is when this person is innocent and we conclude it's guilty. What is the type 2 error? Letting a guilty person go free, which actually, according to the Constitution, is the better of the two. All right, so what we're going to try to do is to control the first one and hope for the best for the second one. How could the jury make sure that they make no type 1 error, ever? Always let the guy go free, right? What is the effect on the type 2 error? Yeah, it's the worst possible, right? I mean, basically, for every guy that's guilty, you let them go. That's the worst you could do, okay? And same thing, right? How can the jury make sure that there's no type 2 error? Always convict. What is the effect on the American budget? What is the effect on the type 1 error? Right, so the effect is that basically the type 1 error is maximized. So there's this trade-off between type 1 and type 2 error that's inherent. And that's why we have this sort of multi-objective thing. We're trying to minimize two things at the same time. And I could find many ad hoc ways, right? So if you've taken any optimization, trying to optimize two things, when one is going up while the other one is going down, the only thing you can do is make ad hoc heuristics. Maybe you try to minimize the sum of those two guys. Maybe you try to minimize 1/3 of the first guy plus 2/3 of the second guy. Maybe you try to minimize the first guy plus the square of the second guy. You can think of many ways, but none of them is more justified than the other. However, for statistical hypothesis testing, there's one that's very well justified, which is just constrain your type 1 error to be the smallest, to be at a level that you deem acceptable, 5%. I want to let go of at most 5%. Sorry, I want to convict at most 5% of innocent people. That's what I deem reasonable. And based on that, I'm going to try to convict as many people as I can. All right? So that's called the Neyman-Pearson paradigm, and we'll talk about it next time. All right. Thank you.